Let's jump right back into the ratio and the root test. So just a quick refresher from the last video of what the ratio and the root test are and how we apply them. So the first thing, if we've got a series and we decide we're going to use the ratio and the root test to determine convergence, we're going to either take a ratio of the terms, a sub k plus 1 over a sub k in absolute value, or we're going to take the kth root. Okay? So we take a limit as k goes to infinity of one of those two things, define a new L. And then if that quantity is less than 1, then we have absolute convergence. If that quantity L is greater than 1, which includes infinity, then a sub k must diverge. And if L equals 1, root test and ratio test are inconclusive and we have to try something else. Okay, so that's our process, and now let's jump into some examples here. So let's take a look at this one. And so this is, we did a couple examples in the last video, so we're starting with our third example here on this video. If we have a series that has a factorial in it, my little thought bubble here, when I see a factorial in a series, something of the form n factorial, which remember, by the way, n factorial can be written 1, 2, 3, out to n minus 1. Times n, just as a reminder of what n bang or n factorial is. Factorials turn out often, if we see a factorial, that's a clue, not always, but that is a clue that a ratio test might be a useful test to apply, because we'll get a lot of canceling in a ratio. So ratio test is a good option. Ratio test is often a good option, just because of the nature of how factorials, when you're doing a ratio of one factorial over another, you're going to get a lot of canceling. Okay, so that's just sort of my little thought bubble. We're headed in the next section into looking at which test should we apply. And so I see a factorial, and I'm more likely than not going to apply a ratio test because of the way things are going to cancel, and we'll see that here. All right, so we're going to jump into it. Let's do it. So let's define our L. L is going to be equal to the limit. In this case, it's n approaches infinity. So it's going to be the limit as n approaches infinity of the absolute value of n plus 1 squared over 2 times n plus 1 in parentheses minus 1 factorial times, and then we have just the original term, the nth term, 2n minus 1 factorial over n squared. All right, I am always careful as I go and I do my plugging in here, because I don't want to drop any constants or anything in the ratio. That will definitely affect my value of the limit. So let's go ahead and jump back into the limit and to the expansion here. And in the expansion, as I go ahead and expand and look at these factorials, I'm going to go ahead and group the two polynomials. So I'm going to write that as n plus 1 squared over n squared. And I'll look at my ratios this way. And then I'm going to have 2n minus 1 factorial over 2n. That becomes 2n plus 2 minus 1. Just kind of writing that so you can see the steps here. So this will be 2n plus 1 factorial. And then I'm going to keep going, keep simplifying so I can take the limit quickly. And I would write this, let's go ahead and just write that as n plus 1 over n, quantity squared, bring that all into one power there. And then let's go ahead and expand out these factorials. So this is going to be 1 times 2 times 3. And then we're going to end at 2n minus 1. The factorial on the bottom is going to start out very much the same, 1 times 2 times 3. It's going to have a term 2n minus 1, but it's going to keep going because it doesn't stop until it gets to 2n plus 1. So then there's going to be a 2n and a 2n plus 1. So it has two additional terms in its expansion. Okay? These two factorials differ by two terms. The one on top is 2 less than, has an expansion 2 less than the one on the bottom. Okay? All right. And then, of course, this is why ratio test. This is why I was saying in that little thought bubble up there, a factorial is often a good option for the ratio test because of what's going to happen right now. And you're going to see we're going to get cancel, cancel, cancel. Everything cancels except for those last two terms of the factorial in the denominator. And then, of course, this n plus 1 over n could actually be written as just 1 plus 1 over n. Quantity squared. And then I now just have 1 on the top here and 4n squared plus 2n. And now I can take the limit, and the limit is this is going to approach 0, and of course this is going to approach 0 as n grows without bound, and we have 1 times 0, which is actually just equal to 0, of course. And 0 is clearly less than 1. And so therefore we can apply the ratio test. So therefore, the series that we were looking at, that n squared over 2n minus 1 factorial from n equals 1 to infinity converges is absolutely converges. Remember that the ratio test gives us absolute convergence. So this converges absolutely by the ratio test. RT for short. Okay? So we have absolute convergence. And we are done. Okay? All right, nice compact little proof right there. Define the limit and then take a look at what happens. Okay, let's look at another one. So if I were to come across a problem like this, so here we've got negative 1 to the k over k squared plus 1. Now, if I just jump right into it and I say, let's do ratio test, right? Like if I jump into it and I go, let's do ratio test, we'll do it exactly like we did in the last one, just to find the limit. K approaches infinity of negative 1 to the k plus 1 over k plus 1 squared plus 1, k squared plus 1 over negative 1 to the k. And then go ahead, finish out the simplification here and take the limit. So just let k approach infinity. We'll have just a negative 1 here, and on the top, k squared plus 1. On the bottom, if I expand that out, I'm going to get k squared plus 2k plus 2, adding the extra 1 there outside the square binomial. Okay. And then what I'm looking at, notice right here, is I'm just going to apply the fact that we've got the same degrees here. We have two polynomials. The degree of p of k is equal to the degree of q of k. The two degrees in this rational expression are the same on those two polynomials, therefore it'll just be the ratio of the coefficients. So we're going to have the absolute value, it is an absolute value, negative 1 over 1, which is equal to 1. Now, that, give it a little like fireworks or something, that's inconclusive. That doesn't tell me anything. So that means that the ratio test is actually inconclusive. So I got to do something else. So you have to try another test. And this will happen periodically. Periodically, we'll pick a test, like the ratio test in this case, to apply to a series, and the result will come out inconclusive, which means we just have to go back and try something else. And so I would come back to this and I would say, you know, let's go back to a little thought bubble here. I would say, you know what, this guy looks an awful lot like the absolute value, I should say this. The absolute value of a sub k, take off the switch. The absolute value of a sub k, which is just 1 over k squared plus 1, looks like 1 over k squared, which is p series. So this is what's going on in my head. And I'm saying it looks an awful lot like a p series. I think a better route here would actually be comparison test. So let's go that route. Now remember, we're trying to find convergence, but we have to classify it as either absolute or conditional. So what I would do on this series is I would say, okay, so let's try again, try comparison. But rather than going with comparison, I mean, technically you could actually go alternating series test, but I want to look at the absolute value of this thing first. So let's try comparison. So let's first do this. Let's look at what the absolute value of those terms are from k equals 1 to infinity. And the absolute value would actually be 1 over 1 plus, I'm sorry, 1 over k squared plus 1 from k equals 1 to infinity. So let's get in there. If that's what the absolute value looks like, then we can set up an inequality. So this is where, notice, k squared plus 1 is actually bigger than k squared, of course, for k greater than or equal to 1, which means that the reciprocal 1 over k squared plus 1 is going to be less than 1 over k squared for k greater than or equal to 1. And of course, these are also positive terms. We knew that we took the absolute value, so these terms are always positive. So that's true. And we know that the series 1 over k squared from k equals 1 to infinity is simply a p series. So this guy converges by p series, where p equals 2, which is greater than 1. All right. So we have everything we need right here to show convergence, because we've just shown that the absolute value of my series is less than a converging series. So let's put it all together in our final statement here. So now we can say this. We can say, therefore, the series that we're looking at, 1 over, actually, let's look at the absolute value first. The series 1 over k squared plus 1 converges by direct comparison test. And therefore, that's the absolute value of the series we started with, negative 1 to the k over k squared plus 1 from k equals 1 to infinity, converges absolutely. All right, so that puts it all together. So we've got convergence of the absolute value of the series, which means that my series that I started with is absolutely convergent. So if the ratio test fails, right, we had a failure of the ratio test right here. Ratio test failed. Use something else, right? So then we got in and said, well, let's do comparison. So the ratio test failed, try something else. We went for comparison on this one. Okay. All right. Let's see if we can get one more quick example in here before we end this video. So here is one more quick example. So if I come across this guy, negative 12 to the nth over n cubed, and I go, okay, let's jump in there and let's do, we could do root test on this one or ratio. I think I'm just going to go ratio test. Let's go ratio test. Limit as n goes to infinity of negative 12 to the n plus 1 over n plus 1 cubed times n cubed over negative 12 to the n. And keep it going. Anytime we've got these exponentials, we get nice little canceling, so we'll get a negative 12 just to the first power, technically over 1. And then I'm going to bring these guys together. N over n plus 1, I can write that cubed. Okay, right there, I can pull those in together. They were both cubed, both those polynomials were cubed, so pull them together. And then I can apply the limit, and the limit is going to end up being negative 12 in absolute value times, now when I apply the limit here, we've got degree p of n. Inside that power, the degree of p of n equals the degree of q of n. So therefore, I'll have just the powers on the lead coefficient, so I get 1 over 1 cubed. I'll write that out, but it would just be 1 over 1 cubed, which of course is 12, but 12 is greater than 1. Okay? 12 is greater than 1, which means, therefore, by the ratio test, this was a quick example, therefore, the series itself, negative 12 to the n over n cubed from n equals 1 to infinity, diverges by the ratio test. All right. So we've got divergence there. Okay, one last piece on the ratio test. So we can apply ratio or root tests. Now we've done a good number of examples and even looked at one when it fails. Remember, we have all of our other tests, so don't forget that we have our other test. So there is one more I find it like mind-blowing. I love this last little piece that comes in this section, because this idea of this infinity and this absolute convergence and the idea of absolute convergence versus conditional convergence. So let's think about this. If we were to take a series, right, and we were to rearrange the way in which we add it up, rearrange the terms. So what is a rearrangement? A rearrangement means we just change the order in which we're adding up the terms. So if we had a finite sum, if we were adding up 5 numbers, we could reorder them in any way. Mathematically, we could reorder them in any way and still have the same sum. Of course, rearranging a finite sum does not change the value of the sum. But is that true? Right? The question would come up, is that true for an infinite sum? I don't know. Well, is it true that if we were to take a sum and add it up, but maybe switch the order? So you can see on this example I did here, I just said, what if we started with the 10th term, and then we added the first term, and then we added the 20th term, and then we added the second term, and then we added the 30th term, and then the third term, right? We rearranged it for whatever reason. Then it has been proven that an absolutely convergent series will converge to its sum regardless of the rearrangement. You can rearrange it in any order and it will still have the same sum. Absolute convergence is very, very strong convergence. Okay? So absolute convergence is the strong, very strong convergence. If you have an absolutely convergent series, that means that it adds up to some sum s, and you rearrange that series in any order you want, you'll still get s. Now, if you have a conditionally convergent series, so if you have a conditionally convergent series, like the alternating harmonic series, turns out that you can pick any real number, doesn't matter, pick any real number, pick your favorite number, and it turns out that there will be a rearrangement that would be equal to that r. So that is meaning it's a weak type of convergence. We can make those conditionally convergent sums equal any sum, which to me is just mind-blowing. So kind of a fun way to think of series, right? They're infinite, right? So whatever sum you want, pull those terms out of the series that would get you that sum, stack those at the front, and put all the other terms, I'm air quoting here, put all the other terms just at the end of the series. And when I say the end of the series, there is no end of the series, it's infinite. Anyway, I always like talking about rearrangements, because to me it's just like so mind-blowing. It's where mathematics becomes really interesting, really fun. Okay, and on that note, I will end with a funny little mathematical joke that that fits really nicely into our series. So I'll leave that here on the screen. I won't even read it. It's a good one. Little humor to end our section on root and ratio test.